So standard free energy change only applies in a narrow set of conditions. So if we're looking at the equilibrium between liquid water and water vapor, delta G is plus 8.59 kilojoules per mole. So delta G is greater than 0. The process is non-spontaneous at standard conditions. So why does spilled water evaporate spontaneously? Yeah, it's actually in a non-standard condition. Because the standard condition for the water vapor is a pressure of 1 atmosphere. Is the pressure of water vapor in this room 1 atmosphere? No, the total pressure of all the gases in the room is 1 atmosphere. The partial pressure of the water is actually very, very small. A lot of times it's like 25 torr out of 760 torr. So really, really small. So then what we're looking at here when the wet floor becomes dry spontaneously, we're not looking at standard conditions. So in those many, many times where we're not at standard conditions, we need to calculate not the standard change in free energy, but just the regular change in free energy under non-standard conditions. And so this is the equation for that. The free energy change is equal to the standard free energy change plus R, which is the ideal gas constant with these units, 8.314 joules per mole Kelvin, times the temperature in Kelvin, times the natural log of Q. Q, we have seen before, Q is the reaction quotient. It's calculated the same as the equilibrium constant, but it's whatever conditions we have right now, not necessarily equilibrium conditions. So if you have a reaction involving gases, you're going to use QP, calculated with the pressures, and you're going to use QC for reactions that have solutions. Any questions? So here we're looking at free energy versus pressure, partial pressure of water, not to scale. In this equilibrium, where we have liquid water and water vapor, K is equal to, well, Kp is equal to the vapor pressure of water divided by nothing, 1. Because this is a liquid, its concentration doesn't change, and so it doesn't show up in an equilibrium constant, it doesn't show up in Q either. So Q here is equal to the partial pressure of water. Under standard conditions, Q is always going to be 1 because of how things are defined. Because any gases are going to be 1 atmosphere. Any solutions are going to be 1 molar. And solids don't show up in Q. Pure liquids don't show up in Q, right? So all you have is 1s. All you can end up with as standard conditions is Q is equal to 1. When Q is equal to 1, then that equation collapses. Because the natural log of 1 is 0, and so this whole thing goes to 0. So here we have Q being 0, and over here we have Q being 1, where we have all the atmosphere is water. So when Q is 1, then we're going to we're going to get condensation. This reaction is going to go in the reverse direction. When Q is 0, we're going to get evaporation. Delta G is negative. And here, where Q is equal to K, we're going to have equilibrium, which is where delta G is equal to 0. Does that make sense? So this appears to be non-spontaneous. That's because the actual conditions are nowhere close to standard conditions. So 25 degrees Celsius, liquid water is in equilibrium with water vapor at a pressure of 0.00313 atmospheres. So that's what Q is equal to. So if we do this calculation here, 8.59 kilojoules per mole plus 298.15 Kelvin times the temperature, no, that was the temperature, 8.314 joules per mole Kelvin times the natural log of Q, which is 0.0313 atmospheres. So what my calculator is giving me for this answer is 3.03. So the calculation is not coming out to exactly 0 because there's some rounding involved. But that would be actually in joules per mole. So in terms of 8.59 kilojoules, 3 joules is nothing, right? It's just a product of rounding issues. So at equilibrium, the reaction is spontaneous in neither direction because it's at equilibrium. It's just going to stay there, right? Now, does that mean reaction isn't happening? No, it is. But they're happening at the same rates, and so the concentrations aren't changing. Any questions? For other non-standard conditions, you would calculate Q and substitute it into the equation. So here we're given a different pressure, and I need to remember what that is, 8.59. 8.59 kilojoules per mole. So delta G for the reaction is equal to delta G standard is plus RT, right?
Yes.
Yeah. Plus RT, so R is 8.314 joules per mole Kelvin. Now, they didn't tell us what the temperature is. What's a reasonable thing to assume? 25. Room temperature. That's standard for this stuff, right? So 298.15 Kelvin. Natural log of Q, which is 5.00 times 10 to the minus 3 atmospheres. And remember, this is joules, and that's kilojoules. So I'm going to do it in joules. 8.59 times 10 to the 3. That's 8.314 times 298.15 times the natural log of 5 times 10 to the minus 3. So I'm getting minus 4544 joules per mole, which would be negative 4.54 kilojoules. So is the evaporation of water spontaneous here? Yes, it is. Any questions? Yes?
So, how one ATM, 1 ATM would K equal 1 to for the evaporation of liquid water?
Well, no, K will equal whatever it equals. Yeah. Any other questions? Yes?
How do the units in this one cancel out? 'Cause, well, at the end we know it's gonna be joules per mole, but how ATM
Yeah.
and everything else
Yeah.
cancel out?
What about those? So, we've got the kelvins cancel out, so that's nice. And we can reconcile joules and kilojoules by just, throwing in 1,000 there. Yeah, so this is a bit disturbing. It works because of how it was all defined to start with. Because, what's the unit when you take the natural logarithm of like a meter,
They get all messed up.
right? It's really meaningless. So my guess is that what it actually is what they did with the equilibrium constant, where you're not actually doing the pressure, you're doing the pressure over 1 atmosphere. And so the atmospheres cancel out. The concentrations are their activities. It's the molarity divided by 1 molar. So actually, there wouldn't be a unit in there. I just thought of that while I was talking. There's actually a good reason. It was a great question. Anybody else? Consider this reaction at 298 K. Calculate delta G under these conditions, and we're given partial pressures. Is the reaction more or less spontaneous under these conditions than under standard conditions? So this is delta G for the standard conditions, right? That's what the little degree sign means. So it was negative 102 kilojoules under standard conditions. So what we need to do is we're going to calculate Q. I'll just write out the whole equation here. So you can calculate Q separately and then plug it in. I like to just make my calculator do all the stuff at once. So I would say negative 102 kilojoules plus, that's not gonna be enough room. 8.316, 314, 316 is my house number. I'm gonna convert this to kilojoules. Kilojoules per mole Kelvin times the temperature. Oh, there's actually lots of room there. Times the natural log of Q. So after the discussion we just had, when we stick these numbers into the equation for Q, they actually don't have units. So Q is going to equal, now this sulfur is a solid, so that doesn't show up. It's the partial pressure of water squared. So 0.0100 squared divided by H2S squared, so that's 2, times SO, which is 1.5. Negative 129. Kilojoules per mole. Anybody else get that? Thanks. More spontaneous or less spontaneous than standard? More spontaneous. So that's what we were asked to calculate, and it's more spontaneous. Any questions?